o'clock. You guys can see my screen, right?
Looks good.
Okay, cool. Let's get started. Okay, it is recording. Good. So today we are going to discuss format string vulnerability, and this is a fun one actually. Oh, I probably forgot to update this slide. Um, so format string vulnerability was discovered back in 1999, maybe 2000, around that time, and it caused a lot of problems. People started to discover many exploitable bugs um, from all kinds of programs, from very small utility functions, from big server functions as well. So this is what we're going to discuss today, and we probably will spend more than one session on this one actually. So before we talk about format string vulnerability, we will first talk about say functions with variable arguments. So what is a function with variable arguments? Basically, it is a function when the developer programs this function. The developer doesn't really know how many arguments it will take. It could be 2, it could be 3, it could be 20. That is only determined by the caller, not the COE. The developer develops the COE, programs the COE, but he or she doesn't know if how many arguments the caller will provide. So so if you program in C, you have been using functions with variable arguments. For example, the printf function is one of the functions with variable arguments, but you probably never noticed them. You never realize that these functions are different from other functions. So the C library function printf is one of those, and there are other ones as well. Especially many of those format string functions, including printf. So to implement functions like this with variable arguments, you can take advantage of the C type. There's a C type called the VA list. VA basically is a variable arguments list, and also there are 3 functions for you to use. Those are not necessarily always functions. Depends on different architecture you're using. Some of the C libraries implement those 3 functions as macros. And let's take a look how this is implemented. So I downloaded this from the internet and this URL. So this is a very simple example to show how to use the variable arguments. So we can implement a function called average. So basically, average is a function that take many arguments, then calculate the average of those arguments. So the input can be any type actually, but the first one is an integer, and this integer specifies how many arguments there will be. Then after that, in the prototype, you notice that for all other arguments, when you develop this, you don't even know their type. So you just use 3 dots here. You don't know the number, you don't know the type, you just use 3 dots there. The return value of this is a double. So in this function, if you develop this average function, the first thing you do is you declare a VA list like this. So this will be a local variable VA list. Then you need to initialize this with the VA start function, which takes the VA list and also the arguments, I would say the last arguments, you know the type. In this case, we only gave one argument here, which is the first argument, we know the type is int, but it's not necessarily the same way. You can develop a different function with many arguments, you know the type. Then there are more arguments, you don't know what they will be. You can develop something like that. There are functions like that, like sm printful, something like that. I will show you later. So the first thing is basically you initialize this VA list and also tells that the last argument, I know the type, is the argument NUM here, the number here. That's finish the initialization. Then after that, you just keep calling the function VA arg. And this one, it takes argument. The first one is the VA list, the second one is the type. So in this case, you just keep calling this. Every time you call this, it returns the next argument. And in this case, in this function, we want to know how many arguments are there. So we specify that in the first argument here. After all this, we call the VA-end to destroy, to uninitialize the VA list. Somehow it should balance a stack or something like that. I'm not sure how VA list, the VA start is implemented because it could be different on different architecture. So when you call this function, what you can do is you can call it with different number of arguments. So here we want to calculate the average of 2, 3, 4, 5. There are 4 numbers. Then we tell the function average, there are 4 numbers. They are 2, 3, 4, 5. Then the second one, we have 5, 10, 15. Then we tell it has 3. Okay. So this is basically how you use this variable argument, how you implement a function with variable argument, and also how to call this. Okay. So if you ever programmed in C++, you notice that this is a little bit similar to one of the C++ feature called C++ function overloading. Okay. However, they are totally different things. I'm going to show you in a minute. So first here we have this code is C++ code. This is not C code. So in the C++ code, we can define 2 functions, and those 2 functions have the same name, has the same return value. However, the arguments are different. The first one takes 3 arguments, calculate the average. The second one takes 4 arguments, takes average. So if you call those 2 functions, it will be the same. So the main function here, nothing is changed. The C version, the C++ version, nothing is changed. But the implementation of this, they are totally different. So in C++, those 2 functions have the same name, but when you compare it, they are totally different functions. They're not the same function. But this one, no matter, this is actually one function. This is one function with different number of arguments. Those are 2 different functions. So I'm going to show you here is I put I added code. Oops, sorry, which folder I'm in right now. Let's see where we are. So we'll go to the cpp. Oh, let's go to the over average function first. So this is an average function. I already compiled it. You can see if we do a object dump of the average function, you can see there is only one function called average. Okay, and the function name in the C code is average. The function, the symbol name in the binary is still called average, and this is how it is implemented. It's not very important. Then we go back to the cpp overloading one. Here we have the cpp overloading one. If we check this, you will find that there are two different average functions. Even though at the C++ source code level, they have the same name, when they are compiled, the compiler will generate two different symbols. So at the binary code level, there are two different functions. And the C compiler generates those function names by adding the argument type there. So that function, the first function there, takes 3 integer, right, as input. So that's why the generated function name is average I means there are 3 integer arguments. And the second one will be I because there are 4 integer arguments. The Z7, I don't remember how they generate that. Of course, if this is a function member function in a class or structure, then the name would be adding some more information as well. So don't confuse those two things. C variable argument and C++ overloading are totally two different things. Even though when we call them, the same similar. Of course, in C++, you can still do that functions with variable arguments. Okay, then next we will talk about format string functions. So format string functions, obviously they use something called a format string. And what the format string functions do is they convert C data types, such as integer, such as double, float. They convert those data types into a string representation. So you need to use the format string to specify the type of data like that. Then the function will just print out that string representation. They can print it out to different places. Could be std out, it could be std error, or any file descriptor. Where do you print out doesn't really matter. There are so many functions can do that. Printf is just one thing. Then like all the functions we looked before, the arguments of this format string functions, obviously there will be one format string, and that format string doesn't have to be the first argument. It can be the second, it can be the third, doesn't really matter. But there could be many other arguments. So all those arguments are still pushed to stack for the 32-bit version. For 64-bit version, obviously we know they use registers. So depending on the data type, the caller function will push either the value or the address of that value onto the stack. For example, if we are printing out a string, we have seen this for many times. If we use printf to print out string, we do not put that string itself on the stack. We put the address of the string on the stack. If we print out an integer, then we put the value of that integer on the stack and not any address of that variable. Okay. So the format string functions, they usually use the format string to determine how many arguments are there. And this can be a serious problem sometimes. If we do a man printf, you will find out that at least printf has many siblings there. You can see all those functions from printf, fprintf, sprintf, snprintf. They are all format string functions. And if you check the prototype, you can see that when you do printf, it will print out things to std out. And the first argument it takes is a format string. It's a constant char format. That's a format string. So if you do fprintf, then you are going to print out something to a file descriptor, to an open file in this case, not a file descriptor. Yeah. So in this case, Um, the first argument we know it's a file pointer. The second argument is a format string. If you do dprint f, then the first one is a file descriptor. If you use sprintf, you are going to print something to a string. And the first argument is the string, the second argument is the format string. So as you can see that the format string doesn't have to be the first argument. It can be the second, it can be the third. The key here is you can have many arguments that you know the type. However, there are more arguments here, which you use 3 dots to represent, that you don't know the type, you don't know the number. Okay, so and the siblings of printf are not the only format string functions actually. There are many more. For example, the syslog function is also a format string function. Arrow, there are many arrow functions you can use, and a lot of servers will use those functions. They are also format string functions. For example, let's do a quick, let's do man syslog. You can see this is the syslog function. Here is a syslog function. You can say that in the syslog function, the first argument you give is a priority. However, the second one is a format string. Also, there are others. For example, this one takes arguments. This one takes VA list. So they are basically the same thing. Usually, this one is implemented. This one is implemented by calling this one. But also printf is usually like that. Printf is implemented by calling vprintf. Okay. So now we know what is a format string function. Then we will spend some time on format string itself. You have been using format string many times. You have been using printf, you have been using other format string functions, but you may not know how powerful those format string functions are, and also how complicated they are, and how dangerous they are. Okay, so it has been in the C library for a long time, and only in, like I said, 1999 or 2000, people discovered that, oh, this can be very dangerous. Okay, so first of all, the format string itself is a C string. So, and it's also an ASCII string. So a C string, an ASCII string end with 0, right? And this format string, first of all, it contains some text to be written. That's just text, no escape characters, just text. But it can also have some escape characters, characters that in this case is called format specifiers. And those format specifiers will be replaced by values specified in subsequent arguments and formatted as requested. So a typical prototype for a format specifier looks like this. It starts with the percentage sign. However, because it's a C, right? I mean, percentage sign in ASCII is 25. So if you say something like this in a string, like a slash, this is backward slash. This is forward slash. Yeah.
No, this is backslash, I think.
This is.
Oh no, this is. Yeah, this is backslash.
Okay. So if you say slash like this, you say x25. This is equivalent to the percentage sign. Okay. So the format is like there is a percentage sign, there is an optional flags, optional width, then a dot. If you want to use precision, then you have to use a dot here. Then there is a length, then there is a specifier. So you have been using the specifier a lot, like you have been using D, you have been using P, something like that. So, but there are some specifiers could be super dangerous here. So if the string doesn't really have a percentage sign, then this is just a format string with regular text. Okay, it doesn't specify what will be replaced, but it can have multiple of those percentage signs. We will go through each of these types because they are super important. We are going to utilize those to carefully design our exploit later. Okay. So after the percentage sign, the only part required is the specifier. Everything in the middle, they are optional. When we carefully choose this part, we can make our exploit. Sometimes we have to use this part to make our exploit possible. Sometimes we just use this part to make our exploit easier to use. Then the specifier part is the part you're quite familiar with. You're familiar with D, you've been using a lot. If you want to print out an integer, then you will use D or I. If you print out an unsigned integer, you use U. And there are O, X as well. Also, there are F for float. Also, you can use uppercase or lowercase. It depends on what you like. And also you can use the scientific notation here. Also other things. Also you can print out a character using C. If you print out a string, you use S. So that's what you have to use, percentage sign S, percentage D. If you want to print out a point address, you can use P, okay? What's really interesting is this one, the N. So how many of you used N before? So anyone used N before? So we have 4 people here. Oh, we have 5. Any of you used percentage N before?
No,
No,
not me.
Okay. This is the extremely dangerous one. Most people do not know this exists. Okay. Before I started the format string vulnerability, I never know you have an N like this, you can do something like this. Okay. So if you have something like percentage N, nothing will be printed out. But you have to give a lot of arguments here. And that the corresponding argument must be an address to an integer. So what it happens is nothing will print out, but the number of characters that have been written so far will be stored back to that pointer address. Okay, I will show you an example later, then you can see. So basically, everything else when you use printf, when you use a format string, you are printing things out, you are writing things to the output. No matter where is your output could be a buffer in memory. Your output could be, for example, S printful or SN printful. The output is a buffer in memory, or it could be a file. It could be std out. But you are writing things to the output. However, this one is different. This one is you are writing things to memory, and you specify where that memory is. You specify that. The last one doesn't really matter. It's like an escape. If you want to print a percentage sign, then you just use 2 percentage sign. And so the N one is very interesting, very dangerous, cause a lot of problems. After this, we will go through the flags and also weights and precision, because they are also extremely important for us to craft smart exploits. Let's see which one I want to show you guys. Let's talk about the weights first. So this one basically tells you tells the function, the printf function, the minimum number of characters. Remember, it's characters to be printed out. So you can use percentage D, or you can use percentage 10D. So if you use percentage 10D, then this function, the printf function, guarantees that it will print out at least 10 characters, even if that integer is only, let's say the integer is 2. It will print out 10 characters. The 2 is just 1 character, right? Then it can be, at the beginning, it can be 9 white space, or it can be 9 zeros, and that is where you specify in flags. So if you put 0 here, then it will use left pad zeros there. If you use a space, then it will pad with a white space. So that's actually a very important feature for us to use later, because we can use this to write arbitrary number of characters out. Okay, the precision similar, but it's more about the minimal number of digits after the period here. Okay, so those are the most important ones, and we are going to say, let me drag this. Do you guys, if I drag this, do you guys, is this blocked for you guys, or how does it work on the screen?
We can see past it.
Oh, you can see that? Okay.
No. We cannot see. We cannot see the block.
It's transparent to us.
Yeah.
Oh, okay. So now I put it to another window there, make it easier for you. Okay. And also there are lengths. This is also, this one is especially important when you do that percentage n thing. This determines the length of the data type. For example, if you do percentage d or percentage n, by default, that's 4 bytes. What if you only want to use 2 bytes, then you use h. Or if you only want to use 1 byte, you can use HH, means half. Okay, so you can say those will be important. But I think today we're not going to use those. But next class we're going to use something like that. So this is basically an overview of the specifiers of the format string. But I gave you guys link here. I think you guys should read this carefully to know all those specifiers. I show you some examples here. We will go through this, and all those examples here we are using printf. Let's say the first one. Those are the things you think you're super familiar with, but sometimes it can get really, really tricky. Okay. Let's see what we have. The first one is we are the format. So the first argument, this is a format string. Then we have 2 more arguments. The second argument is a character A. Then after that is the number 65. So they are almost the same thing. So 65 is in ASCII is actually uppercase A. So what the function printf does is it will go through the format string character by character. The first character is uppercase C. It's not a percentage, so it will just print it out. It will just give that to the output. So everything from here to here, including the white space, will be faithfully outputted to the output. Nothing will be changed. The printf will not change anything like this. Then there's a percentage C. Then the function printf knows, oh, I should look for the next argument and use that argument as a character. That's what percentage C means. So even though here the percentage C, this substring itself has 2 bytes, right? 2 characters, 2 bytes. It will be replaced with something is only 1 byte, which is the character A. After that, there is a white space, so it will faithfully print out that. Then there will be a percentage C again, so it will look for the next argument again. After that, another white space, then a new line sign. So those will be faithfully print out. So technically, after this A here, there is a white space, then new line. That's what it is. So the second one similar, but there are 2 arguments, which one is D and the none. Then this one, those 2 will be print out. The third one is the one we are using with here. Remember, let's go back to the specifier here. We have the specifier, then there's no dot, right? So look at this one, there is no dot here, which means we don't have precision, we don't have length. So everything is a flag and width, okay? So here, the flag can only be those things. The flag can only be plus, minus, space, pound, and 0. It's not that. So this is width. So the width is 10, okay? Which means we're going to print out an integer, and we will make sure that that integer we will print out at least 10 characters. That's what we make sure. And we don't have a leading 0 here. The default one is a white space. That's why the print out here is like this. So we print out 1977, and before that there will be 6 white space. Actually 7, because here there is another white space. This one will be faithfully print out. Then this one will be the whole thing. The 1977 will be replaced. This one will be replaced by 1977 with at least 10 characters. So there will be 6 characters, 6 white space, and another leading white space, then the number 1977. So if we change this with zeros, we just add a 0 here. Then what will happen is, so this 0 is not part of the width, instead it's part of the flank. Okay, so means we will replace the white space with zeros. So here we have 6 zeros, white space, and this number 1977. Any question there? I beg to have any question there?
No, I don't.
Okay, that's what I hear here. Okay, then the same thing for others. You can say you can print out integer with a different how to pronounce that? Brandices? Yeah, maybe. Yeah. So you can do that, and also for float, we can do precision here. So there is a dot. You see, well, there is a dot, which means this is precision, and here the precision is 2, which means we will ignore the 1/6 part, only 1/4 part. So this one print out will be 3.14. And the next one will be scientific notion. This one as well, scientific notion. Then what's a star? I'm not really familiar with a star. What's a star?
Dr. Zhao, I think that takes the 5 and
yeah.
uses it for the white space.
Oh, yeah. So yes. So what a star does is it will look for the next argument and use that as the width. Yeah. Of course, this one, a string is just a percentage x. So those are the basic examples of format string you use. And here we are not using percentage n. The example do not have the percentage n. That's why I created this example for you to try. So this one, let me show you the code. It'll be easier. Where is it? Oh, format string. So you can see here, this is the source code of the example we're using percentage n. Probably too small, make it bigger. Okay, what do we have? We have a function called the foo. There's no vulnerability here. Oh, technically, I'm not sure if there's vulnerability. Let me think. No, I don't think this one has any obvious vulnerability. Okay, we have 2 global variables. One is A, one is B. There are 2 global variables. We initialize it to 0. So when we print out the value, we can say A is percentage D, B is percentage D, then we just print out the value. Then we will use percentage n to change the value of A and B. Okay, so let's say what we do. We do a printf, then we have changing A and B. So everything from here to here is just the regular characters. There's no escape character. So this will be faithfully printed out. And I carefully write this part. This is actually 20 characters, 20 bytes. Okay. So which means at this point, when you say the first percentage n, how many bytes, how many characters the function printf has already written? 20, right? Then that number 20 will be stored in the local variable A. And of course, this one doesn't have to be a local. It can be any variable, right? So the percentage n will look for the next argument, and it has to be an address for integer, and it will write the number it has written so far to this local variable. Okay. So after this A will have the value 20. Then after this, the n itself doesn't print out anything, right? So it will not increase any number of printout. But after that, what we do, we print out 1, 2, 3, 4, 5. We print out 5 more characters. Then we have another percentage n. Then this percentage n will look for the next one, which is the local variable b. So after this, A will have the number 20, B will have the number 22, 25. Okay. After that, we print out a new line sign, but this is after the percentage n, so it doesn't really matter. Okay, does that make sense to you? Any questions here?
Yes.
Okay. So, so you can see this is how we can write things. As an attacker, you probably already get that. As long as we can put some address here, we can overwrite anything in the memory space, anything. But we're not going to do that today. We're going to do this next week. Today we are going to look at other hacks. We're not using percentage n today. So after this, we will print out at B. Then after this, let's say another one. This printf is the same. At the beginning, we have the same string. It has 20 characters. After that, we have a percentage 0, 20d. Okay, remember what does that mean? That means we're going to look for an integer in the arguments, and we will guarantee that we will print out at least 20 characters. If the integer is very small, then we will just add zeros at the beginning. But we make sure that at least 20 characters here. So here, because this one is small, so it will only be 20. So this one is 20 characters. So this one will be another 20 characters, right? So after this, it's actually print out 40 characters. Then there is another white space here. So when we do percentage n, it will be what? It will be
41?
41, yeah, it will be 41. Then we have another percentage n here. And this one, we didn't print anything in between. So the b will still be 41, right? So after this, we expect A to be 21, 41, B also be 41. After this, we have the same thing, 20 bytes here. Then this is how many? I don't know how many. It's 1, 2, 3, 4, 5, 6, 7, 8. Some 8 characters. Then we have this one. Make sure it's only the precision is 2, but the whole string will only be 10 characters. So this part will be 10 characters. So it will be 20, 10, 38. Yeah, something like 38. Yeah, only one. So A will be something like 38. Let's try. Let me make it smaller. Okay, so sorry for just run this. Yeah, it's 38. Correct. So those are the values we get. So the first time we print A and B, it's just 0. The second time we print out this one, we're going to print this, and also 1, 2, 3, 4, 5. There is no white space in between, okay? And A will be 20, B will be 25. The third time we do this, this 50 will be replaced by, will be a lot of leading zeros. So it should be 18 because 0 is 20. So the whole thing is 41 bytes. 41 characters. The reason 41 is here, there is a white space, which is not, it's hard to tell. There is a white space. Okay. Then A is 41, B is also 41 because nothing in between. After this, then this one, the whole thing is 10 characters, but the precision part is 2. Okay. Then this one is 38 bytes, 38 characters. Okay. So that's how. That is how that percentage n works, and even though we're not hacking with this method, but you can see this is dangerous. As long as you can put any address here, this will be super dangerous. You will be able to overwrite anything. Let's say if you want to overwrite the return address on the stack, the canary will not work anymore because this is arbitrary write. This is not the sequential write we had before in the buffer overflow. In the buffer overflow, we have sequential write. There's a canary. If you don't know the value, you overwrite that, then your attack will not be successful. This one, if you know the address of the return address, then you put it here. Then you will only overwrite that. You will not touch the canary. So right. So can be very dangerous. Okay. There is actually something else in the format string, which is the $sign, but this is not in the C standard. So which means it's probably not implemented anywhere, everywhere. Sorry, not anywhere, everywhere. There is a POSIX extension for format string. You can use the $sign. The syntax is you put a number here, then $sign. And the number. So this n has nothing to do with that percentage n. The percentage n, the n is a specifier. You have to use n. So here n is just a placeholder for number. Okay. So n is the number of the argument parameters to display using this format specifier. So this can allow that. Problems we have the traditional syntax is if you have two arguments, then you should have true this percentage sign. What if we want to reuse one of those? The syntax doesn't allow you to do that. If you want to reuse that, you have to specify the argument twice or multiple times. So this one solves that problem. For example, here we can print through percentage sign $2, which means 2 means the number of arguments this one looks for is not the first argument. It's not the first argument after this one, it's the second. So this one makes sure that we're going to look for 17, not 16. And we are going to print out 17 as an integer. Then the second specify the same percentage $2, which means we are still going to look for the second argument. So using this extension, the order doesn't matter anymore, and we can use argument multiple times. So this is just one of the extensions. If you master this, you can also write better exploit. Okay, so I just want to share this so you will not be surprised when you say something like this. Okay, so how can this format string really go wrong? We already know what format string is. We already know how to use it. But this looks benign, right? I mean, how this can go wrong, except that percentage n. The percentage n one, if we say that, you say, oh, this one is dangerous. But how about everything else? How can that go wrong as well? So remember that in a format string function, it is the format string itself. The format string determines and also tells the function how many arguments it should look for. In this case, there are 2 %d here. So in the function printf, it knows I should look for 2 arguments. But at a syntax level, if you do not give it 2 arguments, if you just give it 1 argument, there's no syntax error. The compiler will not. I'm not sure if the compiler can tell that, but technically the compiler can tell that, right? But the compiler will not do that. The compiler will not pass. Basically, the compiler will not pass the format string.
I don't think, would compiler be able to tell? Because let's say we get format string from somewhere else.
Yes.
Maybe a trusted source, like.
Exactly. So you're talking about other cases. For example, what I'm thinking is, if the format string is fixed, then obviously the compiler will be able to tell, right? But there are more cases like you said, the format string could come from anywhere. So at the compiler time, the compiler doesn't really know, right? Uh, so compiler doesn't. So anyway, the compiler doesn't pass this. So compiler doesn't know how many arguments you should put there. Only the runtime, the function, will know that. So it's possible that they do not match. When they do not match, the function printf will still look for those arguments on the stack. That's a problem. Okay, so it could be more of those arguments than needed. It could be fewer arguments than needed. And like you said, the format string may not even be hard coded. The user can even provide the format string. So one of the terrible or wrong usage of this is you just give an input, a user input, and use that user input as a first argument. And obviously that argument will be treated as a format string. If you just use regular characters in that argument, then printf will just print out. But if you have percentage sign, the printf will treat that as a format string. So so that's why also the format string vulnerability is also at the beginning, it's considered as a programming bug. Like programmers are not supposed to use this one. So you're not supposed to directly use something like this, printf with a user input, because the user controls the format string. The correct usage is you always hard code the format string part. Then the user input will only be used as other arguments, not the first arguments. Let's say our first example today. Um, this is a simple example. We have a vulnerable function. Let's say what kind of vulnerabilities we have here. Okay. This is main function. We'll call the vulnerable function. So we have a global variable s, and the function will print out what's your input. Then you will get your input. So obviously this one has a buffer overflow, right? Your input could be huge. Your input could be larger than 20 bytes. When you have larger than 20 bytes, what will happen? You will overflow. You will overflow. Of course, this one I will compare it with a canary there. So if you overflow, it will be detected. Then it will simply just print out this. So do not think about the buffer overflow. What is the problem we have? We are direct. This is exactly the problem we just said. Okay, you are using this program. It's using some user input which you cannot trust as a format string, right? Then let's take a look at the source code. Where is it? Format one. So the source code is this. Then what do I want to show you? Oh, I want to show you the makefile. So in the makefile, you can say I didn't use the node protector flag. I didn't use the non-executable stack flag. So those two functions are this battery is fully protected. So if we run this one, we just put a lot of input here, some garbage here. What will happen? We will say stack smashing detected, something like that, right? Stack smashing detected. So there is a buffer overflow, but the canary were protected from that. However, what can we do with this one? What kind of a damage we are able to do here? Let's say. So this is a binary code. Let's draw the stack a little bit. So the red ones are the things on the stack. So first of all, we have the array S, which is at EBP minus 20, which is 32, 20 in hex, which is 32. So S is here. Then we have a canary there at the same address, EBP minus C, so which is here. So actually, between S2 canary is exactly 20 bytes as we need in the C code. So if you overwrite more than 20 there, you will change the canary, then the smash stack will be detected. However, I also highlight all the instructions that could affect the ESP here. So you can say we have push EBP, push EBX, then subtract, and do another subtract, push blah blah blah. So after all of this, so ESP will point somewhere here, okay, at an address lower than S. Where it exactly points at doesn't really matter, but but we know that the ESP when the ESP is not pointing to S, it's pointing to some lower address. Okay. So what can we do with this? So obviously this is a vulnerability, right? What can we do with it? The first thing we can do is we can print out part of the stack, okay, and we can also crash the program. Um, we can print out part of the stack because we can instruct the printf function to retrieve parameters, arguments from the stack, but we're not providing arguments to it. So we're just reading from the stack and display them. So let's say if we do percentage %x, the reason I put a dot here is just to separate this, right? It's not necessary. Um, yeah, it's easier to show you guys the demo. So now we run this. So ESP. So if we do the percentage %x, just one percentage %x, what will the print function printf do? Printf will look for the next argument, which we didn't provide, but that argument is pointed by the ESP, right? Somewhere on the stack. So it will just print out something on the stack here. Okay, this is basically that. Then we can do this multiple times to print out many things. Here we're going to print out. So first of all, this is 8 character itself. With the new line is 10 character itself. It's a 9 character itself. So these 9 characters will be copied to S, okay? But S is 20 bytes, so this will not trigger any stack smash there, so there will be no problem. Then it will just print out 4 items on the stack, and each of them is 4 bytes. So if we print out this, it will just print out this, okay? This is basic ugly. Okay, we don't even know where's the boundary, which one is which, okay? That's why we do something like with a dot, and you can use anything, right? You can use this, it doesn't really matter. You can use anything. So now how many bytes we're using here? We're using 4 of those, so we're using 11 bytes. So still not trigger any problem. We can do one more, yeah. So if we do this, then we can print out what on the stack one by one. Okay. So this is the first thing on the stack. Go up, there is a 0. Go up, this is this number. When you look at number, what is this? This looks like an address, right? This is a return address. This is probably the return address of what? This return address is the function printf use, right? Then higher than that is this one. The higher than that, there is a number 1 there. I don't know why there's number 1, but yeah, there's a 0, there's number 1. So those are basically, but if you do more, then you probably will have the smash stack detected, because the string you're supposed to give is cannot be longer than 20 bytes. So this one, how many we have? 1, 2, 3, 4, 5, 6, 7. So 7 here should more than 20 bytes. So this one should trigger the stack smashing. Okay. So what else we can do with it? We can do. Yep. You have any questions?
Yes. Why do we see return address of the printf, because shouldn't it be higher than on a stack than, or like it looks for the arguments, right?
Yeah. No, no,
So
no. The arguments we're looking for here is hold on, let me think. Um, okay, let me think. First of all, I'm not sure if that is the return address in printf.
yeah,
Um,
but it does look like, but yeah,
but it could be also be the return address for the upper layer function, right? Let me see.
there would be
So,
buffer, I think.
so we will push the format string there, then we call, so the format string will be there, then we go to that. Um, yeah, I think you are right. It's probably not the return address in the printf. It's probably the return address in um,
Maybe there's some nested function that printf
in root
calls,
function. It's maybe it's the vocal function.
but as in, it still doesn't make sense because it would start showing the char array before it shows the full function return
But which one is
arguments.
that? Which one is the? So this one is not the canary. The canary is always there is a zero there. So
Yeah,
this is not. Yeah.
maybe
Uh,
there is a nested function in printf.
there's a nested function printf.
Maybe.
Oh yeah, that's right too. Because printf has multiple layers. Eventually, it
Yeah.
will call other functions, right? It will call v_printf. Then eventually, the v_printf or whatever will start looking at the format string.
Yeah, and the canary would be it's minus EBP minus C, so it
Right.
wouldn't be right before the return address. That would be EBP of some sort.
Yeah, but there could be
Yeah.
multiple canaries, right? But none of this is a canary. Yeah, that's for sure.
Yeah. Okay.
Mhm. Okay. So what else we can do is another simple attacks. We just use a percentage s. So what will happen? We do this. Then we will treat whatever is on stack there as the address for a string, right? So basically, when we do percentage s, we know what we're pointing to right now is this one. So we will use this one as an address for a string. So we do this, and we're putting on top of some garbage here. Okay. Then, but the problem is here. You can see the next one is 0. So if we have a 2 percentage s here, what will happen? The first one we will get this. The second one we will treat 0 as the address of a string. And we know that address 0 you cannot access. It's a null pointer, right? So when you do that, you will trigger. Oops. Why? Oh, it just printed all this. It doesn't. Is that a? Is that a showing an error there? Oh, so maybe this is especially taken care of, so it will just print it down there. But there may be other addresses here which is not valid the address for string. So if we keep doing this, eventually we should be able to, access some address we should not access, then trigger the segment fault, right? We don't know which one triggers that, but eventually someone will trigger the segment fault. So if you, so this can give us, this is useful in many ways. First of all, just by doing something like this, you can quickly determine, just doing a lot of percentage s, you can quickly determine if the program has a format string vulnerability. That's the first thing. The next thing is this can also be used for attack. This can be used to crash a daemon, and if you crash a daemon, probably the system will dumps cores, and if it dumps cores, if you can retrieve that cores, you can debug that to figure out what's going on. And also in network attacks, there could be servers running. For example, there's a DNS server running. You want to do a DNS spoofing attack, and you want the legit DNS server to stop, right? If the legit DNS server has a format string vulnerability, you can crash it. Then you can use this to crash it. do a DOS attack on that, then you run your own fake DNS. So this is actually quite useful as well. Next. So we are here. What's next? So at least those are something we can do with this. Then the next example is this. This one is what do I plan to do with this one? Somehow I forgot. Give me 1 minute. Thinking here. I'm going to do this. We're going to do we're going to do arbitrary memory read. Okay, with this one. So this one we have a local variable which is 120 bytes. Then we get your input. Then we print out whatever you put there. So this is basically the same as the first one. The only difference is I make the local variable larger, so we can put more format string characters there. That's the only difference. So the idea we have here is, I want you guys to think, how can we, I'm telling you that this program, you can use it. So the previous program, this one, we cannot use it. We didn't even try. I think it's actually the 20 bytes is big enough to do that. But we didn't try to use it to read arbitrary address in the memory space. There is a secret somewhere, okay? We want to read it. We know the address of that secret. We want to read it. So how do we use this one to do it? Any theory there? Just I give you 30 seconds here to think. What can we do?
And you said we are not using %n for this one?
Nope, we're not going to do arbitrary write. We're only going to do the arbitrary read. Yeah. By the way, we compare this with Canary as well, so you can also smash the stack for this one. So if you want to read arbitrary address, what is the first thing you need? I mean, somehow you need to put that arbitrary address somewhere so you know where to read, right? That's for sure. Otherwise, you don't know. You cannot tell where to read. So, but where can you put things? You can put things in the buffer. Okay. You can put the address in the buffer. Okay. Then what is the second thing? Is you need something to read things. Okay. %x doesn't work because %x will only read from stack. Which specifier you use to read other things, to read from anywhere?
P.
Which one?
P.
B?
No, P as in pointer address.
Okay.
The specified P.
P doesn't really read from there. P will print out that address.
Oh, okay.
Yes. What else?
%s.
Yes, exactly. %s. Well, the only drawback of %s is it will not print out your hex. It print out your string. That doesn't really matter, right? Even if that string is not ASCII, it will print out. I mean, if you cannot read that in terminal, you redirect it into a file, right? So that's not a really serious problem. So %s is the one you give an address and it read things from that address for you. And it doesn't only read 4 bytes, it reads until there is a 0, right? So that's what %s do. So then the next thing is, how do you provide the address? Then let's look at this function again. Okay, so this is what the stack look like. For this one, we have the local variable 120 bytes. And if you look at the C code, the temp buff is actually 132 bytes away from the saved EBP. So this part is 100, right? And the buff and the calories actually is 120 bytes, exactly 120 bytes there, okay? So, and where's the ESP? ESP is somewhere here, okay? We don't know where it is. It's here. So, what we're going to do here is we want the printf function to we want to construct something like um, printf. Let me write it let me write it here. We want to construct something like this: printf, then $s, then the address, right? This is how we want to print out this. The address we don't. We're going to put on the stack. Then %s will also be on the stack actually. So what we're going to do is we are going to write the address somewhere here in the buffer. Then we will net the pointer to point to that string when there is a %s. When printf is going to pass %s, we make sure the pointer that looks for the argument points to that. The pointer is not necessarily ESP, but the pointer will look for, we're pointed to that string. Then that address. Then printf will use that address as the address for anything that you can read from it. I guess I didn't explain it very well. Then let's just look at the code.
Am I the one lagging, or is there a Wi-Fi issue?
No, we froze.
We froze. Okay.
You guys froze.
Hey, Dr. Joe, we lost you for about 30 seconds.
Really? 30 seconds?
No, not 30. Probably like 10 seconds.
Okay. How about now? Can you guys see my screen?
Yeah, right when you started typing in terminal.
Okay.
Okay.
So what we have here, let me show you the make file. Okay, we have all the protections for this one. Then we have the main we have the code. So the code is we have a main function. There are two global variables, just two strings. Two global variables are two pointers to point to two strings. And we print out that the secrets are at, we use %p to print out the address. We print out the address at this place, printers also. So the goal is to use format string vulnerability to print out the string. Okay. So if we just run this program, what will happen? It will print out those two addresses for us, right? So if we just do whatever, then what will happen? It will do nothing. It will just print out the string because there is a printf. Just will print out the string, nothing else. Okay. If we do a %x, what will it do? It will just print out things on the stack. So if we do a lot of %s, it will just keep printing out things on stack. That's it. Okay. So if we just or if we do %s, we do a lot of %s, eventually we trigger a segment fault. Okay. The goal is we want to print out those two strings. So how do we do that? We can try something we can do is let's see. Oops, what I'm doing. Okay. So what we can do? It's better we use print out this to a file first. Let's say print we want to put the address. Let's do one first. Well, let's put the address there. So it will be 08 70 55 56. So if we print out this, what will happen is then give this as the input. Then at the beginning of the buffer, we will have this address written there, right? This is the address we written there. So if we give this to the exploit file, then we do the fs exploit. It will not do anything, right? It will only print out what is at the temp buffer, which is that address. But that address can be interpreted as a string like this. So that's a string there. Did I get it right? Yeah. So basically, if we do XXD, the exploit, you can say that is the string we put there. Okay. So what we want to do next is what else we can do? We can put oh yeah, this is wrong. I missed the exit. That's why it looks a little weird. Okay. So now, if we do a %x, then we will print out what is on the. So if I do a lot of %x here, eventually what I will get? What do you think I will get?
The address of the start of the buffer.
Exactly. We will get the address, right? We should be able to say that because at the beginning it points to somewhere here. When we keep getting %x, and we go up every time we go by 4 bytes, then eventually we will say our address there, right? We don't know how many, but if we keep doing that, we should be able to say the address 5655 70080. So if we do this, that's too big. Okay, that's better. Do this. Do you see our address? Oh, it's here. You see? That's
Yeah.
our address. So how many %x we have been using? Here we used 1.
4.
Oh,
3.
No, I used a lot actually. 1, 2, 3, 4, 5, 6. Yeah, I used the 6, but actually it's just 1, 2, 3, 4. So the fifth one are going to point to our address, right? So which means if we only do 4, we should not be able to print out our address, right? That makes sense, right? Okay. So if we do this, it will not point to our address. But we know that at this point, the pointer inside the fprintf is pointing to our address. We're not retrieving it. Okay. If we retrieve it, we will basically we ask printf function to use that var macro function to retrieve this. Then we will get that address, right? So the next step is very critical. So what do we put here?
%s.
Exactly. We just put %s here. At this point, we are already pointed to the correct address, pointing to the value we want. We just want to treat that value as an address and retrieve whatever is there. And we do this, then we should be able to get our string. So now we read the string. Does this make sense to you guys?
Yes.
Okay. So what if we want to get the second string? What do we need first? We still need the address, right? So we put the address. So we put the address here. What is the address again? 1A 70 55 56. Okay, that's what we need. Then the only thing we need is another %s, right? Nothing else. because this percentage S will consume the first address, 4 bytes, then the second percentage S will consume the second 4 bytes. Make sense? So we do this, we should be able to print out both strings. See, this is what we print out. This is the first string, this is second string. Of course, we print out things we don't want. That's the part we cannot fix because we are printing things. The printf will print things from the beginning of this, and the beginning of this is the address, and actually 2 addresses. Then we also have percentage %x for us to move the internal pointer. So this is how we print out 2 strings. Make sense?
Yep.
Looks good.
Okay. Good. Then the third example will be a little bit more complicated. Yeah, so I actually put it here, and obviously it will be different on different machines. So you can use some signs here. Another thing is sometimes you could be 1 byte or 2 byte off, right? That's easy to fix. You just add things here at the beginning. So your address could be 1 byte or 2 bytes off, 3 bytes off. Then you just add things in the beginning, add some padding there to fix it. And this part doesn't matter. I added this just to make it look better. So this doesn't really change things. For example, whatever you want here, it doesn't really change things, right? Just to make things look a little bit easier for you. Right? So you will print out this, but, the same thing. So the next one, what we're going to do. Okay, so this one, we are going to get a shell, okay? So this is our vulnerable function. And this function, we don't have canary there. We don't have a non-executable stack. But the non-executable stack part is not really important. I mean, because even if the stack is non-executable, we should be able to use return to libc. So that's not really a problem. I just want to make things a little bit easier, so I make a executable stack. So this is a vulnerable function. We have 2 local variables, buff1 and buff2. So buff1 is at lower address. No, hold on. Oh, buff1 is at a higher address, buff2 is at lower address. Okay. Then we have fgets to get data from stdin. But we are only getting 99 characters or 99 bytes from stdin, and we put that in buff2. Okay. So if you put more characters here, what will happen? It will only put 99 characters in buff2. So it's not like it's very easy for you to buffer overflow this one, right? However, the problem is after this, you have another sprintful. The sprintful, the first argument is the string you want to put as the output. The second argument is the format string. So you are actually using the buff2 as the format string and put the output in buff1. Okay. So I said there is no canary. We can buffer overflow this one, but what's the idea you have? How do we write? Basically, what we need to do is buff1 is 100 bytes, right? We need to find a way to write more than 100 bytes in buff1.
Yes.
So if our input at the beginning for stdin is, let's say, 50 bytes, regular characters, then that 50 bytes regular character will be treated as the format string, but there is no percentage sign. So basically, this is basically a memory copy. Then that 50 bytes, 50 characters will be copied to buff1. So it cannot trigger any buffer overflow, right? How can we trigger any buffer overflow here? Before that, let's take a look at the stack first. This is a binary code here. This is a stack. From the binary code, you can see that the buff2 location is from the safety EBP is 208 bytes. Buff1 is 108 bytes. So buff2 is exactly 200 bytes here. Buff1, there is 8 bytes of padding there. That's it. So that's what the stack look like. Okay. Any idea how do we do this?
Can we take advantage of the fact that we can arbitrarily make leading spaces or zeros using the
Okay.
format string, so we don't have to use as many characters, but could make something stretch as many as like 100?
Exactly. That's exactly what we do. But that leading zero or white space doesn't really matter. What matters is the width. Yeah. So you are touching the right thing here. So, but you were talking about the flags using zero or white space. But what actually is the width part, right? Is this part?
Right.
Yes, exactly. For example, this one. If you do 10D or you do 10D, doesn't really matter here. For example, what here is, look at the percentage sign 10D. This is only 4 characters, right? This is only 4 characters. But the output will be 10 characters. Then if you add this percentage 100D, there will only be 5 characters. But the output will be 100 characters. So that is how you do this. So what we want to do is, where's my stats? You want to add something to buffer. You want to, so we know buff2 will be our format string. So our format string will be something like that. So let's try this. This will be format string. So let me show you the makefile first. So this one, there is no canary and the stack is executable because we're going to use share-code there. Then we have that fs3. Let's first try to just get a buffer overflow. Okay, so let's do the percentage %d. It will not trigger anything. So should this print out something? Why is not even print out something? Oh, this one is not print out something because we just print this to buffer1, right? So we're not use we're not use printf. So so we will not be able to say anything in terminal. So if we do percentage %10d, that thing will be treated as a format string in the second, in the sprint flow, not in the get here. So it will generate 10 bytes to buff1. That's not enough to trigger any buffer overflow. Okay, if we do 100d, still no. Then let's do 101d. Oh, this is not enough. Oh, remember here. So this part is 108, right? So probably 109 will trigger buffer overflow, but 112 is definitely, 13 will definitely trigger that. Yeah. So let's try 100 and what, 8? Oh, 100, yeah. So when we do 108, we actually trigger buffer overflow because maybe there's a new line or something. So that will overwrite 1 byte at a safety EBP and trigger that. So 107 should be, so 107 should not be problem. But even 107 is problem. Why is that? So this is 108.
Wait, can you go back?
Sure.
So you have 107, so the plus those 4 characters at the very beginning, right?
Well, it should be +4 for the %d.
What?
It's 107d. So it should be like +4 to 107.
No, I don't think so.
Wait, isn't D no, never mind. Never
Yeah,
mind.
yeah, we probably need to debug to figure out why this one is, but it's not very important anyway. Huh. Let's try 106. I don't feel this is super important anyway, so 106 works. See, but 107 doesn't. So
We have a
I
null
think
character we need to consider.
no, I think probably we're like which one were you using? Were you using fgets here or?
F gets.
Oh, I think fgets were added two characters here.
That for the file descriptor? No, that's not.
No. The fgets were so whatever you input there, fgets were add two character. One is OA, one is the new line. So the new line basically there is two character, not one. That makes sense.
Which
So-
was the character that's not new line? You said 0A?
One is 0A. There is another one. Yeah, 0A and let me. Um, what is the best way for us to debug this? I think that's a problem. That's a reason we can do this. We can do GDB fs3. Then we set a breakpoint and then do right. Then where are we? How can I spell that? Is a symbol. Oh, we're not running it yet. When are we supposed to give the input data? We can run it. Now we're here. We are gaining fcats. So let's just run to 1, 2, 1 b. So we're doing fcats. So fcats should be the same. 2, 1 b. 2, 1 b. Okay. So we are going to, let's just give a percentage 10d. Then let's check what is our let's do kilobytes. Kilobytes should be enough. At EBP minus it's EBP minus D0. Okay. So my theory is we give it it will print out a 10 like a longer for 10 characters. After that, the fgets itself will append another 2 bytes there. Could be OA something, I think. Let's see. So 1, 2, 3, 4, 5. That's weird. Why is this? How many we give it? We give 10. Oh yeah. So 10 we will have a leading zeros. So 1, 2, 3, 4, 5. 1, 2, 3. Then why there is a 9 there? So are we? Oh no. No, this is fgets. Okay, sorry. So the first argument is not the buffer is not here. The buffer is what is fgets? Fgets the first argument. Are you guys still here?
We're here.
Okay.
Yeah. Sprintf is that where we copy?
Oh yeah, yes, it is correct. So it is here. But we are printing out. Oh yeah, you're right. Yeah, sorry. We need to go to the sprintf, not fgets. Yeah, there we go. We should keep going. We need to keep going after sprintf. Then check the buffer of sprintf, not to the buffer. So here, then we go to 6c. So that's basically buffer 1, right? We need to see what is in buffer 1. So in buffer 1, we have this character. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So this is the number we print out is 10 bytes. Then I think there is a OA and 00. So those are the 2 bytes added there. So it's not just adding 1 byte. is adding 2 bytes. That's what I'm talking about. 0A and 00. So because we're adding 2 bytes, when we do 107, we actually overwrite 109. So 1 byte of the saved EBP is changed. So when we do 106, we'll actually overwrite 108, and that doesn't change anything of saved EBP. Make sense? I think that's a reason. Yeah. Make sense to you guys?
Sounds good.
Okay, cool. So that's it. Where are we? We were, okay. So now we know that we can trigger a buffer overflow. Let's do like 200. Okay, now we know we can trigger buffer overflow. Okay. The next thing we want to do is we want to get a shell. So, any idea how to do this? How do we get a shell?
Can we just tack our shellcode at the end of a expansion of that many decimals?
Okay, but what else do we need to? So right now you say we can actually overwrite from here to arbitrary none, right? We can overwrite. So basically here we are bypassing. The source code here has a limit that you can only write 99 bytes, but in fact we can write as many as we want, right? So to do
We
that,
can return to our environment, right?
yes, we can also do that. We can do return to deep sea because since we can override from here to anything, then we can override the return address, right?
Yep. So we just add the base pointer coverage, and we should be able to execute a normal attack.
Yes. So what we can do is we can have a exploit. There are many ways to construct this. I will construct it maybe this way. Let's see. First of all, from here to here, we will just put garbage. So buff1 to save the EBP, we just put garbage, right? Then from the return address, and this garbage will be how big? This garbage will be 112 bytes. So we will use the approach we just used, percentage 12, percentage 112D to generate this garbage, which will be 5 characters in our buffer. Okay. Then we still have like 98 bytes characters for in our buffer we can use. Then we need the 4 bytes of the return address, right? 4 byte of return address. So after that, we can put some knobs here, and also our shellcode. Does that make sense? But the knob cannot be too big because we can only write. Because we need to consider the first time we do fgets, the buff2. Because everything we first need to put the format string and the shellcode, everything we need to put in buff2, right? But buff2 is only 100 bytes. So that string cannot be too big. Does that make sense?
Conversely, there's nothing stopping us from putting our shellcode in the original buffer and then returning back, right?
Which buffer?
So the buffer that we write into prior.
Yes, we can do that. Yes. So what we can do is yes, you're absolutely right. So technically, the approach I just described, we will have we will actually have 2 copies of that shellcode, right? One is in buff2, one is on top of this, right?
Right.
Okay, and you can return to here or you can return to here. Either way is fine. Yes, either way is fine. Then for remote attack, what you can do is you just do a lot of brute forcing to do using a lot of guess, because a lot of thing is you need to know the address of your shellcode, right? That part you can just do guessing, try it another time. But since we are doing locally, we're not going to guess. We just use GTB to find that out. Then we try this. So this is the shellcode we're going to use. Let's try this. Okay. So we are going to we still want to put things in a local file first. So let's do print. Oh, we need to find the address first, right? So we use this one. We use r.s to balance this, to make sure the stack is consistent first. And do fs3 evolve foo. So now we are in evolve foo. So here we just, what do we need to do? We just print out ESP. Right? We just print out ESP because this is the beginning of evolve foo. We haven't pushed the EBP move ESP yet. Now this is where, so this is the address of the return address, right? This should be the address for return address. So if we try, this should be the return address. See, this looks like an address 5655. So this is basically the return address. So we are in evolve foo. So this is basically the return address in the main function. So this is a part we want to overwrite to our own share-code address. And also, this is also the address for our, kind of like for our share-code, yeah. Something like that. Okay, remember this address, P016, okay. P016, something there. Now we are going to do our looks like my internet is not stable. How about now? Can you guys hear me now?
Seems good.
Okay. So now we are going to, we're talking about buff2. But eventually buff2 will get to buff1. So we're actually thinking about buff1 here. So from here we want 120 bytes of garbage. So we can do percentage 112D. Well, I mean, D doesn't really matter, right? You can do F or whatever you want. So that will be the 112 bytes of garbage we need. Then we need so now we can override the return address. So our plan is to put the share code somewhere on top with some knob. So the return address right now we know that is D01C. So we just add a little bit that D01C, then probably add several bytes there and 2C there. Hope that's not too much. Depends on how big our knob can be. Then we have D0, FF, okay. Now we have this. After this, now we overwrite this. We already overwrite. Now we overwrite the return address. Now we can have knob. So we can have knob, which is 90. I don't know how many bytes we can have, so we save it there. Then we have our share code. Just copy it. Before. Oops. Oh, this is stupid. I copy it. We have this weird symbol here. Okay. So this share code, how many bytes is the share code? The share code is 28 bytes. Here is 1, 2, 3, 4, 5. 5 bytes, 33, 37. So we should have, 6 bytes should be okay. 6 bytes of knob should be okay. Let's just try this. So this is our default. Okay. Then, do you guys remember how do we do this again? How do we give this to our program?
Do we pipe it with cats?
Yeah, we need to, first of all, this is what we want, right? We want this, so we need to do a cat, right? We pipe, we do cat, exploit, and we do another cat, let's try. Oh, it works. Oh, yeah, it works. The first time we do it, it works. Okay. Do you guys understand what's going on here?
Looks great to me.
Okay, let's change a little bit. Let's change this 60 to 70. What will happen?
Think you're gonna break past,
So when we have 70 here, the problem is
or you're gonna get trimmed rather, right?
exactly we will not be able to put the full share code there, right?
Yep.
So yeah, so for to this, it's not supposed to work. So see, we get a segment fault. Okay. That's because we can only copy the beginning. We can only copy 99 bytes, and we need to make sure this string is smaller than 99 bytes. If we make this knob smaller, let's say if we do not use knob, this will not work because this address will be pointing to the middle of the share code. So this will not work as well. Right? Also get a segment fault, right? But as long as our knob is big enough, I think 10 bytes should be enough because I added 16 bytes, right? So 16 bytes, probably 16 bytes or 20 bytes should be enough. Let's try 16. Oops, it's the X here. 16 may not work, I think. Oh, it works. 16 works. Okay. The key here is, when we do all kind of attacks like this, we always use we always reverse engineer it, try to understand every byte. But in a lot of real attacks, you don't really have time to do that. For example, if you're in CTF, you don't really have time to get all those addresses accurately. What you want to do is you even prefer to write a program, and the program can just simply try. Yeah. But at least for this semester's class, I want you guys to understand exactly what's going on. Oh, by the way, next semester I'm also offering a similar class, but it will be advanced. We were talking about some more advanced techniques, more programming there. But it's a seminar class, so it's a bit tricky. Because a seminar class, some people will take it as 3 credits, some people can take it as 1 credit. Then I need to decide how much coding you need to do there. Okay. So that's basically what I have for today. Any questions?
None from me.
Okay, good. So the exploit for this one will look like something like this, and you can try this later.
Can we use our own shellcode now that we spent so much time making it?
Of course, of course. Yeah. Okay. So for next class, several things we're going to discuss. First one is we're going to use that percentage %n. That one is interesting. That one can overwrite arbitrary location, and we will use that h thing. So the h thing to overwrite, sometimes overwrite 1 byte, sometimes to overwrite 2 bytes, sometimes 4 bytes together. And there is actually, I was looking for it. So when you use percentage %n to overwrite things, someone very smart come up with a equation or formula, should be formula. Someone come up with a formula to tell you what you want to write. You input what you want to write, you input where you want to write. Then his formula will generate a percentage %a specifier, and with different ways, different those HH. But I couldn't find it anywhere. I tried to Google that, I couldn't find it. So before next class, I need to find out that formula. I used it before, but now I cannot find it. So that is one thing. So also next week, I think we probably will start talking about use after free vulnerability. Basically, it's you malloc something, you free it, then you forget you already freed it. Well, sometimes it's not you forgot. It could be multiple threads, right? Then one thread freed it, other thread can still use it. Then there will be other vulnerabilities. So that will be the first time we touch heap vulnerability actually. Okay, any questions for today? If there's no other questions, we will stop here. Thank you very much for being here. I didn't really expect you guys to be here. Oh, how many people are here? Just two of you?
Yeah, just me and Avik.
Okay, cool. Thank you guys very much.
Have a good one.
Talk to you
Have a
soon.
good one. Bye.